In this lesson, percentage yield of a chemical reaction, we're going to look at how we can determine the percentage yield of a particular reaction. This is going to give us an indication of how efficient our experiment was when we performed it in the lab. Let's start with an analogy. At the bottom of a cookie recipe, there's always a report of the yield of the recipe. And when you read the yield of a recipe, so for example, if it says the recipe yields 5 dozen cookies, what that's telling you is that when you do this recipe, you expect to be able to bake 5 dozen cookies. If you've cooked cookies before, you know that it's really difficult to actually get as many as they suggest you're going to be able to get. So for example, sometimes when I bake cookies, instead of making 5 dozen, I may only be able to make 2 dozen cookies when I use the recipe. So what's happened in this scenario is that I baked 2 dozen out of a potential 5 dozen cookies. If I want to report that as a percentage rather than just saying I baked 2 out of 5, I can say I baked 2 out of 5 times 100, and that will give me a percentage of 40. So in this particular scenario, I have a yield of my cookie recipe of 40%. So let's look at what we did here. We took the 2 dozen, which is how many cookies I actually baked, and we divided it by 5 dozen, which is the number of cookies that I should have been able to make. And this is what our formula is for percentage yield. To find the percent yield, we're going to take the actual yield and we're going to divide by the theoretical yield times 100. In an experiment, the actual yield is the actual amount of product that you obtained after doing the experiment. The theoretical yield is what you should be able to obtain, and we find this in chemistry by doing mass calculations. So the problems that you've been doing in the previous lessons, the mass problems and the limiting reactant problems, you were performing a theoretical yield calculation. So although we're giving it a fancy name, really it's what we've been doing already. Now there's lots of reasons why a percent yield might not be 100%, and chemists will try to improve the procedure that they carry out in order to optimize the percent yield. We want to make sure that our reactants are pure, we want to make sure that we don't lose anything during the reaction, and we want to make sure that the reaction is able to go all the way to completion. The first example that we're going to do was done as a demo in class. And what we were doing was burning a piece of magnesium. We started by taking the mass of a piece of magnesium, and we found that the mass of magnesium that we were going to use in our experiment was 0.50 grams. Now, in burning this in oxygen, the reaction will be magnesium plus O2, and the product of this reaction will be MgO. When we balance this reaction, we get coefficients of 2 in front of the magnesium and the magnesium oxide. So this is the experiment that I did in the class, and what I did was I burned 0.5 grams of magnesium, and at the end I measured the amount of magnesium oxide that I produced, and that's the actual yield. Before we look at the actual yield, let's look at what the theoretical yield of magnesium oxide is. The theoretical yield is the mass that I should be able to produce when I burn 0.5 grams of magnesium. And so what you might notice here is that this is a mass to mass problem. We've got the mass of magnesium, and we want the mass of magnesium oxide. So in our flow chart, we know that we need to use the mass of magnesium to find the moles of magnesium, use the ratio to find the moles of magnesium oxide, and then find the mass of magnesium oxide. So the first step in this reaction is to find the moles of magnesium, and we do that by dividing by the molar mass. So it's 0.5 grams divided by 24.31, which is the molar mass of magnesium, and we get 0.02 moles of magnesium. Now the ratio between the magnesium and the magnesium oxide is 1 to 1, so the moles of magnesium oxide is equal to the moles of magnesium. The third step is to find the mass of magnesium oxide. The mass of magnesium oxide is equal to the moles of magnesium oxide times the molar mass of magnesium oxide, which is 39.3. And in this case, we find that we get 0.825 grams. It would be a really good idea for you to make sure that you're also doing the steps along the way so that you understand where the numbers are coming from for this question. So by doing our regular mass-to-mass calculation, what we found is that when we burn half a gram of magnesium, we should be able to produce 0.825 grams of magnesium oxide. The next thing we do is to actually perform the experiment. And when we performed the experiment, what we found is that the mass of magnesium oxide that we measured was only 0.45 grams. So we obtained 0.45 grams out of a possible 0.825 grams. We can take this information and find the percentage yield. The percentage yield is the actual yield divided by the theoretical yield times 100. So when I actually did the experiment, I got 0.45 grams. What I should have been able to get was 0.825 grams. So the actual yield divided by the theoretical yield times 100. And the percent yield here is 54%. Now this isn't a very good yield. And when you get a yield that's not close to 100%, you look to the experiment and the procedure that you did, and you want to look for errors that may have led to a percentage yield that was this low. So in that first example, we performed an actual experiment. In the second example, you'll be able to see what a problem will look like when you are solving one. So in this example, it says when 45.8 grams of potassium carbonate is added to an excess amount of hydrochloric acid, 43.6 grams of potassium chloride is obtained from the reaction. The other products are water and carbon dioxide. Calculate the theoretical yield and the percentage yield of the reaction. So as always, the first thing that we need to do is write the reaction. Potassium carbonate has a formula of K2CO3, and we're going to add an excess amount of HCl. The products are potassium chloride, carbon dioxide, and water. So if we want to balance this equation, we have 2 KCl and 2 HCl. So what we're given in the question is that we're going to do an experiment with 45.8 grams of potassium carbonate. And when we actually do the experiment, it tells us that 43.6 grams of potassium chloride is obtained from the reaction. Now the wording of these questions is a little bit tricky, so you need to do lots of practice so that you can identify what is the actual yield in these problems. Words like so many grams is obtained, or so many grams is collected. These are words that tell us that an experiment was done, and that was the actual yield of a particular product. So this is telling us that the actual yield of potassium chloride is 43.6 grams. The way that you know that you need to look for the actual yield is also part of reading the problem. When you read the problem and it asks you to find the percentage yield, you know that you're going to need the actual yield. And so it must be somewhere in the problem, because you can't do an experiment in order to solve a problem. So once you've got the actual yield, you want to set that aside. We know that the percent yield is going to be the actual divided by the theoretical times 100. So we want to first calculate the theoretical yield prior to calculating the percent yield. In this case, because I'm given the mass of potassium carbonate, it is a routine mass-to-mass problem to figure out the mass of potassium chloride that is collected in this experiment. I encourage you to take a moment, pause the video, and determine this mass so that you can practice, and then you can unpause the video and watch my solution. If you're having trouble, okay, watch the solution slowly, okay, and make sure you're following along with your calculator so you know how to do the steps. The first step in a mass-to-mass problem is to find the moles of the K2CO3, which is done by taking the mass and dividing by the molar mass of K2CO3. Okay, these problems are quite multi-step, so we want to carry lots of significant digits. We get I apologize. It's 0.33. Just going to cross this out. It's 0.33138 moles of K2CO3. Step 2 is to use the moles of K2CO3 to find the moles of KCl. The ratio between these is 1 to 2. For every 1 mole of K2CO3, I produce 2 moles of KCl. Therefore, if I have 0.33138 moles of K2CO3, I will produce X moles of KCl. Cross multiplication gives me an X value of 0.66275. I've got double the amount of KCl. Step 3 is to take the moles of KCl and multiply by the molar mass of KCl. So the moles of KCl, 0.66275, times the molar mass of KCl, which is 74.55. I get 49.4 grams. So this is the theoretical yield. This is the amount of KCl that I should be able to get when I do the experiment. So my last step in solving the problem is to find the percentage yield. And the percentage yield is my actual yield. So when I did the experiment, I obtained 43.6 divided by the theoretical yield, which I calculated at 49.4 times 100. And the percentage yield that you get is 88.3%. So that is how you solve percentage yield problems. On the page that you did this example, you can see the textbook questions that will allow you to practice this further.